Here we go. This is a exam coverage for grade 10 advanced first term, covering most of the points that came in the exam coverage. So starting with the main point or the first point, they ask us to apply the equation of the period of a pendulum to calculate the period of a simple pendulum for a small angle oscillation. So that's the main equation, where the period t equal to pi square root of L over gravity. L represents the length of the pendulum. So every time L is longer, as you see here in the black, the period t will be longer. Okay, as you notice, the blue one, which is the short, the period is too short. So for a small cable or for a small rope, the period is too short, maybe taking 1 second to make one cycle. However, in the black one, it's taking maybe 3 seconds to make a cycle. So every time the length of the rope is more, the period is more. Moving on to the next part, we're talking or discussing the Hooke's law. So we need to apply Hooke's law to calculate the force exerted by a spring. Okay, so main equation here, where the F, the force of the spring, equal minus kx. X represent the extension of the spring or the compression, and k is the spring constant. For each spring has its own k, and minus because spring always act opposite to the main force. So it means that if I'm compressing the spring want to stretch, and if I'm stretching the spring want to compress. So it's always opposite to the main force. The other equation of the spring, which is about the energy, so here force is in Newton, here the energy in Joule, which is equal to half kx square. So here the extension, or x, is to the power of 2. So here is a small example. A spring with a constant K equal to 144 Newton per meter is compressed this time by this length, 16.5 centimeters. So of course we have to convert it to meter first of all. So the question is, what is the spring elastic potential energy? So to do that, we apply the equation half kx square, and k is given 144. After converting 16.5 to meter, we got 0.165 to the square of 2, or to the power of 2, sorry, which is equal to 1.96 joule. Moving on to the third point, where we have to sketch a snapshot for the superposition of two overlapping waves. So here we have several types of waves that we want to discuss. So if you look at the green, both waves are on the same phase. They go up and down together. So the sum of them will be constructive. So the amplitude of the third wave here of the resultant will be higher than both of them. However, here in the blue, both waves are in the opposite. So when the first one is in the maximum, the second is in the minimum. So they will cancel each other. So the resultant here is 0. And that's what we call bidestructive wave. In the book, they gave us, or they discuss an example where incident wave with an amplitude of 3 centimeter is facing another wave with an amplitude of minus 1 centimeter because it's down. So the resultant here is 3 minus 1, and the resultant is 2. And that's what we mean by superposition of waves. Moving on to point number 4, differentiate between transverse, longitudinal, and surface waves. So this is an example of transverse wave where the wave go up and down. Okay, the amplitude is moving up and down. Okay, that's what we mean by a transverse wave. On the other hand, here the longitudinal wave, the amplitude is moving back and forth on the same line, on the same axis, but the amplitude is moving back and forth to the front and to the back. And that's what we mean by longitudinal wave. A good example of longitudinal wave is the sound wave. Okay, what about the surface wave? Surface wave is a combination of these two waves, longitudinal and the transverse. So transverse is going up and down, and longitudinal back and forth. So this combination will give us a circular motion, a circular pattern. And that's what we mean by a surface wave. Point number 5, talking about experiment using a number of musical instruments, the perception of sound depending on different physical quantities like amplitude and frequency. So yeah, here in the blue, we see two different waves. So what's the difference between both of them? It's the amplitude. When amplitude is more or amplitude is different, we're talking about the loudness. So more amplitude means the sound is loud. Okay, if the amplitude is low, means the sound is weak. Okay, so that's about the amplitude. What about the frequency? Here, these two waves in the red have the same amplitude but not the same frequency. Okay, so if you have high frequency, means high pitch. Okay, so pitch of the sound depends on the frequency. Here, low pitch. Okay, so again, the only difference here in the blue is about the amplitude, in the red it's about the frequency. Here is a small question about this point. So what physical characteristic of a sound wave should be changed to alter the pitch? So to change the pitch means we have to change the frequency. What if we want to change the loudness? So we have to play with the amplitude. Still with the sound wave. So here we have to describe the sound level and define the decibel as a unit of measuring the sound level. So please take note, decibel is always describing the sound level. And here in the spectrum in the book they gave us an example in differentiating between sounds from 10 decibel, 30 decibel till 140 decibel, which is too loud and too noisy. It's the sound of jet engine. Okay, and the lowest here barely audible, it's 10 decibel, means we can barely hear it. Okay, so and that's the spectrum of decibel, which is again measure the sound level. Moving to question or the bullet number 7, exploring the meaning of resonance, especially when talking about the pipes. So here I pick question number 13, talking about a 440 Hertz turning fork is used with a resonating column to determine the velocity of the sound in helium gas. If the spacing between resonance, so again, every time they say resonance, okay, so we have to remember that the wavelength is divided by 2. So every time we have wavelengths divided by 2 means we have a resonance. If it's divided by 3 or other number, okay, then we don't have a resonance, only divided by 2. So so it's equal to 110 centimeters. So of course we have to convert this to meter. This means the resonance, which is wavelength over 2, equal to 110 centimeter, which is equal to 1.1 meter. So now we already know the wavelength, which is 2 by 1.1 equal to 2.2 meter. That's the wavelength. But the question is to determine the velocity. So V equal, you already know this equation, V equal the velocity equal to wavelength multiplied by F. So wavelength already calculated, multiplied by the frequency, which is 440 Hertz. And the velocity at the end is equal to 970 meter per second. That's a quick short way to calculate the velocity. Moving to point number 8, talking about or discussing the beat frequency. So to calculate the beat means we need to calculate the difference between the two source of frequency. So by subtracting their values, but don't forget the absolute value. Okay, so the beat frequency is always positive. So it doesn't matter if it's F1 minus F2 or F2 minus F1 because we have the absolute value. So again, to calculate the beat, we have to make a subtraction between the frequencies. Moving on to bullet number 5, where this distinguish between electric conductor and insulators. So of course you already know that in case of insulator the electrons will not move easily. That's what we mean by insulator. So we can look here at the red picture where electrons are stuck in the orbit. They cannot jump to other electron, or sorry, to other atom. However, here in the conductor, the electron can go from one atom to another easily. Okay, more easy. That's what we mean by a conductor. A good example of that is the metals, the family of metals. And what about the insulator? It's about the plastic and wood. All of these are example of insulators, or electric insulators, I mean. Okay, one of the most important parts here, question 10 or bullet number 10, demonstrate an understanding that the work performed is moving a charged particle in an electric field can result in a particle gaining electric potential energy or kinetic energy or both. Okay, we'll see here. So they are discussing the term of work. So you already know that work, which is what the unit is joule. So work is equal to the force F multiplied by the distance. So F in a Newton and distance per meter. Okay, so that's one equation, which is the work. The other equation that you already or you have to know is the electric potential difference. Okay, which is delta V. So delta V equal the work divided by the charge Q. So we already calculate the work, and then by dividing the work into the Q, the charge, then we calculate the potential difference, delta V. What if we combine these two equations together? So we replace W, or the work, by Fd. So that's what we get. So by combining the two equations, by replacing the work by force by distance, and we already know that the force F over Q, remember, the force divided by Q is equal to the electric field E. So now the new equation is delta V equal to the electric field E multiplied by the distance. It's highly important, this equation, and here we are doing one application on that. So an electric field intensity between two large charged parallel plates is 6,000 Newton per Coulomb. So that's the electric field E. The plates are separated by a distance of 0.05 meter apart. So what's the electric potential difference? Again, electric potential difference is delta V. So delta V equal to the electric field E, already given, multiplied by the distance. So 6,000 multiplied by 0.05, and the answer is 300 volt. Moving on, so I guess here talking about the electrostatic force and Coulomb's law. So use the vector addition to calculate the net force on a charge due to other point charges, and solve equations regarding that, or Coulomb's law. So again, Coulomb's law is about F, which is in a Newton, equal to K constant, Coulomb's constant, multiplied by first charge by second charge QA QB over R square, over the distance square. So here is this example. The electrostatic forces of two charges spheres are held at distance R. So they are separated by a distance apart from each other. Compare the force of sphere E on sphere B with the force of B on A. So these two charges exert a force on each other. First of all, both charges are positive, means that they will repel each other. So the first force is away from A, and that's what we call it by force of A on B. Okay, so it's to the right. Okay, force of A over B. And the second charge caused by B over A. So as you notice, these two forces are equal. Okay, they have the same magnitude, the same length, but they have opposite direction. Okay, so that reminds us of Newton's third law, action or reaction, which is they are equal but in opposite direction. Okay, so FA over B equal FB over A, but in opposite directions. Moving on to question number 12. again discussing about Coulomb's law. So here we have a negative charge of -2 by 10 power -4 Coulomb, another positive charge by 8 by 10 power of -4 Coulomb, separated by 0.3 meter. So what is the force between the two charges? So of course here we have two charges, means that we have to apply Coulomb's law. And here we go, the given Q1, Q2, and the distance 0.3 meter. So asking for the force. So what's the force equal to? It's K, which is the 9 by 10 power of 9, multiplied by the first charge by the second charge over distance square, which is equal to 16,000 or 16 by 10 power of 3 Newton. That's a quick application on Coulomb's law. Here I guess question, point number 13 and question 3 are talking or discussing the same idea, same point, on the distribution of charges in a metal. So explain how electric charge are distributed on a sphere's conductor and the effect of this on both electric field and electric potential. Okay, so here we have to know, and here also describe the charge distribution of a solid conducting sphere, a hollow conducting sphere, and a regular conducting sphere, and calculate the electric field strengths. All right, so the first picture talking about conducting spheres. So here, as you guess or as you see, the charges are well distributed, evenly distributed. So the negative charge, they are well distributed in the object or in the metal or in the sphere. Okay, what about a hollow sphere? Means it's empty from the inside. So of course, because it's empty, so the charges will gather at the peripheral of the sphere, outside of the sphere. Okay, on the last layer of the sphere. Okay, they will occupy this area only, or this surface only, on the outside, because it's a hollow sphere, it's empty from the inside. So what if we have an irregular space or irregular sphere surface? So in this case, the charges will be concentrated or condensed in the small area, as you see here. So when the area is small, the charges will be close to this space. So for example, here on regular conducting sphere, like this shape here, an oval, the charges are close together at the sharp points. So as you see here, we have 3 charges on a very small point. This will lead us to question number 61. In a television picture tube, electrons are accelerated by electric field. So talking about electron and electric field E, which is 10 to the power of 5 Newton per Coulomb. So we have to find the force. So if you remember the force, first we write the given. So the force is equal to electric field multiplied by the charge Q, because already electric field equal force divided by Q. So we replace by their numbers, electric field 10 power of 5 multiplied by the charge of electron. That's why it's negative. Minus 1.6 power of 10 minus 19. And the last answer is 1.6 by 10 power minus 14 in Newton. All right. Okay, here describe Millikan's oil drop experiment and explain how it confirms that charge exists in discrete amounts. Okay, we'll see this in part B, and which are integral multiples of elementary charge. Yes, of course. So this is an example from the book, example problem number 4. So we have an oil drop, as you see here. It's suspended. Okay, I redraw or I sketch again the given. We have a drop of oil which is suspended. Suspended means hanging here in the middle between the positive and the negative. So the drop of the oil don't know whether to go up or down. So every time you see this word suspended, means we have equal forces. Fe, which is the electric force, okay, or the electrostatic force, equal the force of gravity, which is that wants the drop to fall down. That's the force of gravity. So the question is, question A, what is the net charge? So we need to calculate Q. So starting from this equation where the electrostatic force equal QE, equal the force of gravity. Force of gravity is already given. It's 2.4 by 10 minus 14 Newton. Okay, and E, as we discussed in previous slide, E equal delta V, the electric potential energy, divided by the distance. So a simple arrangement of the equation you got, or you can use, of course, the calculator, and the answer is equal to 6.4 by 10 minus 19 Coulomb. Now, what about part B? We'll see. So, in the upper plate, if the upper plate is positive, how many excess electrons are on the oil drop? So we need to see or calculate how many electrons this drop contain inside. Okay, so to do that, we have Q, which is the total charge of the drop, calculated in part A. Q equal NE. N is the number of electrons. So the total number of, or the total charge is equal electron, the elementary charge electron, multiplied by a number of electrons, N. So here asking how many electrons. So of course talking about N. So N will be equal to Q over E. Q equal to 6.4, 10 minus 19, already calculated in part A, divided by the elementary charge. Okay, divided by this number, and the answer is 4 electrons. So this drop of oil contains 4 electrons. Moving to question 15, talking about the capacitance. The difference across the plates, and it's measured in farads. Apply the equation for the capacitance to solve numerical problems. Okay, we'll see. So first of all, you have to know that when talking about the capacitors, we have one equation that we change depends on the given. So Q, which is equal to the charge, equals C, the capacitance, the symbol of the capacitance, multiplied by the voltage. So you can play with the equation accordingly. So here, for example, the capacitance C equals charge Q over V, the voltage. And what do you notice from this graph? That every time the voltage increases, the charge in the capacitor increases as well. It's a positive direct relationship. So when the voltage increases, the charge increases as well. It will follow, of course. I think, yeah, we did an application on that. So question A, 27 microfarad. Okay, remember farad is the unit of the capacitance, the capacitor. And micro is 10 minus 6. As you see here, it's 10 minus 6. Has electric potential difference of 45 volt across it. So we have the voltage, delta V, and we have the capacitance. It's given 27 microfarad. So the question is to calculate the net charge, Q. So when you see charge means, of course, the Q. So Q equal, remember the equation in the previous slide, where Q equal C, the capacitance, multiplied by delta V. And the charge is equal to 1.2 by 10 minus 3 Coulomb. Here moving to the written question, I believe. So determine the wave properties such as wavelength, speed, frequency, amplitude, speed using graphical and visual representation. Explain the okay, great. So to do that, I pick question number 15. So a sound wave produced by a clock chime is heard 550 meters away. Okay, so someone is producing a noise or a sound away from us as 515 meters. Okay, we can hear that after 1.5 seconds. Okay, so question is, based on these measurements, what is the speed of this sound? So we have to prove the speed of the sound. So this is the given first of all, distance, time, and speed. So to do or to calculate the speed, equal distance over time. This is a very old equation. I'm sure you already learned in previous cycles or previous years. So where the speed equal to the distance over time, and the distance is in this case is 515 meter divided by the time, which is 1.5 seconds. So the speed of the sound in the air, we prove it as 343 meter per second. What about the second part? The sound wave has a frequency of 436 hertz. So what is the period in this case? So to do that, it's just the inverse. This is the simplest equation in physics. So to calculate the period, it's the inverse of the frequency. It means 1 over this amount, 436. So the period is 2.29 by 10 power minus 3 seconds. That's the period. And in the last part, asking for wavelengths. So again, wavelengths is equal velocity divided by the frequency. Velocity already calculated in part A, 343, divided by the frequency already given, equal to 436 hertz. And the wavelength of this sound is equal to 0.78 meter. Moving to the next part, talking about, I guess, on Doppler's effect. Yeah, so I picked for that question number 4 because we didn't discuss Doppler effect in previous slides. So I think we have it's worth giving it this question. So we have a submarine which is moving toward another submarine at 9.2 meters per second. So one submarine is moving towards the other and emitting a sound or ultrasound of 3.5 megahertz. Okay, so the question is, what's the frequency would be? What frequency would the second sub, which is at rest? Again, very important. At rest means its velocity is zero. So the velocity of the second submarine is 0. It's not moving. Okay, so the speed of the sound water at the depths of the submarine is moving at, so that 1482 meters per second. That's the speed of sound in underwater. So we have, of course, we have to use Doppler's effect, and that's the given. Velocity of the submarine 9.2 meters per second. Frequency emitted is 3.5 megahertz. Velocity of the detector. Detector means the velocity of the second submarine, which is 0. How do I know it's 0? Because they say it's at rest, not moving. And of course, the velocity of the sound underwater is 1482 meters per second. So applying, I guess, of course, Doppler's effect. So that's the equation where the force, the frequency of the detector, that's what they are looking for in this question, equal the force of the submarine, the frequency of the main submarine, which is 3.5 megahertz, and multiplied by velocity of the sound, given here, 1482, minus the velocity of the detector, which is 0, over the velocity of the sound, again, which is 1482, minus velocity of the submarine, means minus 9.2 meters per second. So the two submarines, they are coming close to each other. So this means the frequency, the main frequency here, have to increase from 3.5 to 3.52, I guess. Yeah, equal 3.52 megahertz. I think that's it. A quick attempt to revise the exam coverage for grade 10 advanced. Thank you for listening and hope you all succeed in that exam.